Hello everybody, Mikael is my name and I'm going to talk a bit about programming in the C language and how we do that and how it works and some stuff around that. So let's move on here and see what kind of agenda I have. Well, here I have it. So let's start somewhere with an hello world. And I'm going to talk a bit about the C language just to give you an overhead of what it is. Let's review its features, its standard library, so we know what we can expect from it. And let's also talk a bit how it's compiling and linking, executing the program, and in what environment is it executed. So let's check that also. Before we start, actually, let's think about how the different programming languages work. And here I have this at the top. So we have this C language, which is a compiled language. We have a compiler, and we need to create a C compiler for each architecture that we are sort of working with. And the C compiles to something we can call machine readable object code. We can compare that to Java or C#, where the program there with the source code, it's compiled into something that is called bytecode. So that is a higher level bytecode that is compatible on all architectures. And then they have a virtual machine that is executing this bytecode, and this virtual machine then needs to be aware of what kind of architecture it's working on. So in that sense, it's the virtual machine that sort of is architecture dependent. And then we can compare this to the interpreted languages like Python, PHP, JavaScript, and more, where we have the source code it is not compiled, it is just interpreted by an interpreter. And line by line, the interpreter reads and executes the code. We could actually have a look at an overall architecture on this, how it looks like. So here I have made a picture where we have C, C++, that is compiled languages. So there we compile the source code down to assembly. Then we create object code from the assembly code. Then we link the object code to an executable, and then we execute it. Java and C# then, we take the source code, we compile it to bytecode. And then the runtime environment executes the bytecode so it can be executed onto this architecture. And take this interpreted languages, Python, PHP, JavaScript, where the source code is interpreted by an interpreter, which reads the source code line by line and executes the lines. Okay, so this is the differences between different programming languages and what kind of sort of architecture they have, and there are pros and cons with these different layouts. So it might be good to have this sort of image in the back of our mind when we sort of compare the different languages. This is an hello world. It's a great way to start when we learn a new programming language. So on top here we have the include. We include a standard io.header file. So that is a way to get access to the sort of standard library, which includes functions we can use when we create our code. Then we have a main function, so we should always have a main function. Currently this main function returns void, that is, it returns nothing, it takes no arguments, and it just does a call to the printf function, and it prints this function string hello world. Good place to start. And if we want to make an executable out of this, we take that source code we had there and we put it into an hello world.c file. So the source code is put in a .c file. And then we can take that C file and compile it And here I'm using a GCC compiler. It's a GNU compiler for C. And I compile the code, and it will result in an a.out file. That is the default naming of the executable. So now I have an a.out file, and I can execute that like I do in the bottom there, where /, that is just in the current directory, execute the file a.out, and there we go, hello.world. Well, hello world. Good start. This is, they say, or I think I read somewhere that this is the original Hello World program. Not only for C, but the original Hello World. Well, it's from 78. I'm not really sure that is correct, but maybe. Still, it's just a fun fact. They wrote this Hello World on a piece of paper, and they sort of framed it, so now it's a bit popular. Labeled to be the original Hello World. Pretty much like my Hello World, actually. The C language could be, we could say it's a pretty popular language. Here we have a survey, or it's the index from Tioba, where they compare the most popular programming languages. And if we should refer to this particular sort of result, they say that the C is on top. So we have C on top, and we have C++ on 4. And we have more languages you might be aware of. Java second, Python third. We have C# on the 5, Visual Basic, C# and Visual Basic, that's Microsoft Windows. Then we have JavaScript, PHP, SQL for databases, and then we have at the bottom there assembly language. Well, it's not the bottom because it's a long list of programming languages. So it seems to be that C is rather popular. This is an historical view of it, and the blue part up there, I can't really point at it, there, the blue part, that is the C language. It has a dip down there, I don't know why, must be something wrong in the investigation, I guess. But the C language is rather popular, it stays popular over time. Oh yeah, it's a popular language. But when we take this sort of ratings on things like programming languages, we need to be a bit, well, critical. How did they actually compare this? We should always be critical when we see this type of stuff. And so this Tioba, they're checking the search engines to see how much hits they get, and sort of evaluating the rating of the programming language by using the data from the search engines. So that is how they do it, and we should relate to that when we compare a language. But still, I do think that C is one of the most widely used and popular languages because it has an area where it's very, very useful. The C language, well, developed 72 at the Bell Laboratory. It was mainly developed to create utilities on Unix, small program utilities there to help when working with the Unix system. It was a successor to B, so obviously there was a language prior to this, so I guess it was an easy task to name this C language. It has been standardized a few times, and 89 standardized by ANSI and ISO, and that is the version of the language that I will sort of mostly aim at when I'm looking at it here then. Here we have Dennis Ritchie and Ken Thompson, the guys who sort of created the C programming languages. Ken and Dennis, just fun fact, this is how they looked like. Unix people and C people. Yeah. Just fun fact. The features of the C programming language, well, we say it's a general purpose language, so we can use it to do, well, whatever. It's good for that. It is declared as an imperative language, which means that the statements in the program changes the program state. The program state here means the value the variables are holding, so that is the program state. It is a structured programming language because it has this control flow if for a while, and it has block statements. It is also categorized as a procedural language because we can organize our code in procedures or functions, that is. We call it a cross-platform portable language. Since the source code that we develop, we can write that to be cross-platform and portable among several architectures. We just need to take a bit care to know how the different architectures is working, and we compile it down to each architecture. It is rather popular since it has this low-level access to memory. We can freely access the actual memory, so that is a strong point in some sense. And it maps very efficiently. So it's a small language and it maps very efficiently to machine instructions. So it's not too hard to create another compiler for C language down to a new architecture. And maybe it's easy to code and it's more portable than assembly. That is for true. So it's one step above assembly, perhaps. Maybe that's why it's it's one step above assembly, but it's still, since it's such a small language, it's rather close and easy to get down to the assembly and from that down to the object code. Here we have an overview of the standards. We see that it's created 72, 78. We got something called Kernighan and Ritchie C, so an extension of it. 89, then we got this ANSI ISO C standardization, which is also labeled C89. And then we have a few other standards that are adding small bits and pieces to the language, but it's still a rather small language with a small standard library. They're still working, so we have a next major release coming up here. I think it was in December 21 or so. Like any other languages, the language has reserved words, and it's nice to know about this since we cannot use these when we declare variables or functions. So these are reserved words. We don't need to go through them all out to break case, char, const, but quickly review them just to be so you know that these are reserved words and I should not use them for variables. That is fine for now if you do that. So let's see a bit about the bits and pieces in the C language. We have a control flow. And this is a control flow that I think you will recognize in any language you have before then. So we have the if, else if, and else statement. We have loops like for, while, do while. We have the switch case statement, and we have break, continue. And these you generally see in any type of language. They're quite basic, I would say. Here is a list of data types, and let's just quickly review them at this stage. C language is a statically typed language, so we define the type for each variable at compile time, and then that variable should hold the same type all through the execution of the program. When we do operations, or when we execute, when we do calculations or use return values from function, there might be some implicit conversions between different types, and we can also do explicit conversions between the types, but let's leave that for another session. About the data types, then we have character. It's a one character, it's one sort of byte, and usually holding then a value between what is it, 2 to 255. Then we have strings, which is a null terminated char array. So it's an array of characters, and the last character should be a null \0. That is the null terminated or the null character. We have integers, and we have different types of integers depending on how large the number should be. We have short, we have int, which is the standard way. We have long, and different variations of these. And they contain then, could contain, well, how large should my integer be? You should select a matching data type for it. We have single and double precision for float and double. We have a bit more advanced data types where the struct could contain several variables. The union is another more advanced data type, and so is the enum type. We have arrays with a bracket then, so that is an array of integers or array of float, array of double, array of characters, where we have several values in a row, and we can access them using this sort of bracket array notation. Then we have pointers, very interesting and area of the C programming language. You might have heard about C programmers that think that it's really hard to work with the pointers, and well, maybe it is because it's such a area where your program can fail. But if you just get you in order in this star and the address in the address button there, then we will learn how to differ those and how to use them, and then I think you will be quite comfortable with the sort of pointers area also. And finally there we have the constant, we have the defines, so that is to define a constant value or some other define a sort of short macro or some small type that we want to work with. So constant and define. So this is an overview of all the data types we have in the C, and we're just moving on here with the types of operators, and these are also equal to, I guess, any general programming language you might have seen before. We can do a lot of calculations, we can do assignments, we do Boolean logic with not and or. We can do conditional evaluation with a question mark, and this conditional evaluation is could also be called a ternary operator in another language you have. Question mark, colon. We do testing on equality, we call functions, we do increment and decrement, and more on these sort of basic operators. Of course, we have like bitwise calculations also, which is, well, we are in C, so you might want to use that. This is just to show off, it is not specific in C, but this is, like you see these two, this is, well, the same issue in any programming language we have. So the first one there is an equality check. We are checking if E is equal to the expression of B plus 1. On the other line there, we see that A equals B plus 1, so that is an assignment. But that will still work, so both these expressions are fine to write, no problem in the compiler. It is just that the second there, it is actually an assignment, so is it really that you want to do there? And why it works in the second one is that the assignment operator, it leaves back sort of the result from the assignment is also the result from this expression as a whole. So you might see code like that are supposed to be like that. So could work. But keep an eye on those type of constructs, and usually you want to do sort of an equality check when you do like this. We have functions in C where we sort of name a block of code which we can call, and in each of these functions then, or in the block of code, we can declare local variables. We can also access the global variables that are defined somewhere else. We can send parameters or arguments to the function, and we can do that by value or by reference. By value is a sort of copy the value into the function, and that argument can then be used within the function, and even if we change the value, that will only be visible within the function. But when we work with reference, then the intention is to send an argument, send an argument into the function and maybe change its value. So it persists its changed value after the function has returned. And then we often use this references, argument by reference. Then we can change the value within the function. A function should return a value or not at all, fine. And we can have functions that are recursive, that is functions that are calling itself, and that could be a good way sometimes to sort of solve an algorithm. And we can also work with pointers to functions. So we can declare pointer that is pointing to the address of a function, and then we can sort of send this pointer around, and we can use that to call that function. So that could also be helpful in some cases. We have, of course, comments, same type of comments that we have in many other languages. One row comment // and we have the many row comment that starts with /* and then comment and ending up with a */. We have a rather small standard library in C, so maybe that is one reason why it's actually popular. So it's a small basic standard library, and it is sort of structured in these header files. So here we have an example of it's like 10-ish header files, that is. So we have standard IO for input and output. We have C type that helps us test what a character is, what a variable contains for type of characters. We have string for string manipulation and memory manipulation. We have mathematical functions. We can do sort of convert between numbers, allocate memory areas. This is more. We have for diagnostics above there, assert, standard arg. We can jump around. If we really want to do that with set jump, we can deal with signals in the operating system. We have date and time function, and then we have some type of limits and float values, constant for different types. So this is basically the complete standard library for the sort of C programming language. If I really want to know what type of include files I have on my system, I can do like this. Now I'm on my terminal here in my Unix system, and I'm taking my compiler, and I'm just checking where the C processor, usually labeled CPP, where it actually looks for the include files. So here I have, we see the include files with these. I don't know what it's called now. Sorry. With these. That means that the include file is locally to my program. So that is my own include files, and when I include them, they usually start looking at the directory where I am. Then we have the include files with the less than, greater than, and that's where the system include files are. And here we see that my compiler is looking at several places for the different include files. So if I want to see what type of include files I have, I need to look at those directories. And here I did find some of my standard include files by checking my directory user include. and listing all the include files starting with st. So this will of course look different on your setup, but sometimes it might be very helpful to know where you can actually find these include files. Because you maybe, well, it is a good way to look into them. So open them up in your text editor, review their content. You can see what defines they have. You can see how the functions, what functions they have, and how you can call the functions, because you see the function declaration and about the arguments there. So do not hesitate to review the source code for these include files. It's a good source for learning the C programming language and what can be done. So let's have a note about memory management. C is, like we said, low. It deals with low memory management, or it provides an access to directly into reading the memory. So that's a strong point, but also a bit dangerous when we does it wrong. So static memory allocation, that is what is allocated for the objects that is declared in the source code, and they are sort of written into the binary at compile time. So perhaps my string like hello world is an example that is actually put into the binary. Automatic memory allocation, that is temporary objects that is stored on the stack. And that could be, for example, when we call a function. And so the arguments that we are sending to the function, that they are sort of stored on the stack. And when we go into the function might have local variables being declared, and those are also saved on the stack. So the stack is sort of a, well, it is allocated as we go on, as we go by. And when the function returns, well, the stack rewinds and pushes out those objects that was only related to that sort of function call. And we can compare that to dynamic memory allocation, which is blocks of memory that we can sort of request and allocate in runtime, like using a malloc function or something like that. So these are then allocated on the heap, and they will persist there until they are removed or freed by us. So there is no automatic garbage collection in C. We need to do that ourselves. So with power comes responsibility to keep the memory clean, consistent. So I talked about the stack and the heap. So let's take it once more then. The binary has the code to execute and statically allocated objects. So that is the binary. It contains the code plus some data variables defined in the code. When we try to execute it, sort of something happened and the program counter executes the code in the binary. And when we come to something that the sort of a function call or a variable declaration, these are pushed to the stack. So they are allocated onto the stack. When we return from a function, we are popping the stack. And then we have this heap where the dynamic memory allocation is done. So that is a stack and heap, two different memory areas of our executable. Let's just see a bit about compiling and linking and how it works. And here I'm just doing a quick compiler. I'm taking the source code, I'm compiling it, and I'm running my executable a.out, and it's just printing out hello world. Fine. All the compilation in one sort of step. But I can also do this stepwise. And here I do it. So I'm adding the flag -c that says, okay, create the object file, nothing more. So the first step there is taking the source code.c to an object file .o. And at the second step there, I'm then linking the object code into an executable. So I'm taking the object code.o and I'm linking it to an a.out executable. So here I divided the sort of compiling and linking process in 2 steps. And it's actually a 4-step process this. So it's about doing a first, what is done is a pre-processing. So the preprocessor takes the source code and walks through it, sort of evaluates all defines, evaluates all includes, and then we come to the compilation step where we compile the source code down to assembly code. And this assembly code then, in the third step, will be compiled or assembled down to an object code. And at the last step 4, we do linking of all the object codes into an executable. That is the sort of the steps that is done within the compiler. The resulting file, let's have a look at them. So I'm using here, I'm still on my Unix terminal when I do this, just to be able to investigate a bit more. So I see I have resulting files. I have the C file, which is a C source, just a text file. And then I have the O file, which is an ELF file, relocatable for the x86 architecture, not stripped, so it contains a bit of extra symbols. And then I have an a.out, that is also an ELF file. It's an executable, this one. And same about the architecture, and it's not stripped, so it contains some symbol data. Okay, so let's also see about this, told you about this linking area, and let's see what the difference is between dynamic linked and static linked. So here I have an example. I'm trying to show that. So the first one there is it's just compiling our hello world program. So I'm compiling it and I'm using the command size to see how large the executable is. And so I get a size of it on the different areas in the file. And then I'm using the loader LDD to checking out what the executable actually contains. And it contains references to, in this case, three different libraries. These libraries are called .so, and these are the libraries that when I execute a.out, the loader will actually try to find these libraries and load them into memory and execute my executable. The other example here is when I use -static to compile, and then that is a statically linked executable. Here is not dynamic, so when I execute this, everything is in the executable. And this is, can we see when we check out the size for this a.out, that is a much larger size, since all these 3 libraries then are included onto the same executable. And when I do an LDD on this one, it just said it's not a dynamic executable since it does not have any additional libraries to include when I run it. So statically and dynamically linked, they differ in size, but they also differ in when they are executed. So a dynamically linked must have access to its libraries when it's run, and a statically linked does not need to have access to the libraries, but it's a larger one and it's sort of self-contained executable all in one piece. My examples when I'm working with this, I usually work with a make file. That is a text file. It's a build tool that will help me compile the C programs, and when I'm having a large set of C programs, that will help me to only compile the bits and pieces that has changed. So this is a sort of a bit of a tool that could aid in the programmer's day-to-day business if you chose to work on sort of the terminal level. You sort of download a program from sort of some open source program you want to download to your operating system and compile it. It usually contains a make file. So you say like make build or make all or make test. And we have these targets to make it easier to work with this type of projects. If you are working in an IDE, an integrated development environment, you might not sort of use these types of make files because the IDE may be sort of fixes that for you. When we do then compile the stuff, we might get compile warning. So here I'm doing make, and you see what type of it's GCC -g main. So you see what the actual sort of compiler command is running. And here I'm having 2 warnings and division by 0, so it's not allowed. But warnings will still be able me to create the executable and run it. So here I'm trying to run it, and I get a floating point exception since I'm dividing by 0, so not good. But compiler warnings, the program might still work, but most likely you want to fix them. Compare this to compiler errors. When we compile a program and we have some type of error, that is a sort of a disturbing circumstance, so we cannot actually create the executable when having these compiler errors. So here I am written a while loop in a wrong manner, so I don't get an a.out. I need to fix that before. And we can always see what line and what column the compile or the error or warning are, so that will help us. Just go to the right place, see what the error or warning is trying to explain to us, and just fix it. And if we don't, well, sometimes the program compiles without errors or warnings, but we will still get a trouble saying, well, it failed. Perhaps it's doing like this, segmentation fault. Tough call. No hints on where it is. These things just happens. So then we need to sort of adapt some debugging skills to actually try to figure out what was the actual problem with this. This type of runtime errors that sort of might be useful. We saw a segmentation fault here, and that is in general when we attempt to access a restricted area of the memory. So it's a memory access violation. It is a valid area of the memory, but we cannot access it. So that's when we get the segmentation fault. We can also get a bus error, but that is in general raised by the hardware, and that's saying that our process is trying to access memory that is not physically possible to address. So it's a corrupt, incorrect memory address we are trying to sort of read, and then we get a bus error. Core dump is good to know when we talk about this, because that is generally a file that if you have done some settings in your operating system, you will generate a core dump file when a process is failing with a segmentation fault or a bus error. That is, at the moment it fails, the core dump file is created as an exact sort of snapshot of the whole process in memory at that time. And that is really, really useful for us to debug a core dump file when this happens. So debug core dump files, that might be a good thing to learn when we want to be a really good C programmer. And when we have a core dump file, we need a debugger. So this is a command line debugger I just want to show you here. It's gdb, the GNU debugger. And we just debug the file. When we debug a file, we need to have compiled the file with the debugger flags, so the debugger symbols is available in it. So we cannot strip them out, because then we cannot debug it. The debugger depends on some kinds of symbols and knowing how the source code looked like when we compile it. So a an executable that is compiled with the debugging information is in general takes larger size on disk than a executable that is not compiled with the debugging information. So, well, this is like any debugger. We just run the program, we could step through it, we could inspect the variables, and yeah, actually try to debug it and see what actually happened. So debugger is good, but if you were using a sort of IDE, you usually have this built into the IDE, so it's a rather easier perhaps for first-time users to access the debugger in an IDE. Development tool in general. I talked about IDE, and here I just wrote out the code blocks IDE. That is a IDE where we can develop C code, and that could be installed on Mac, Linux, Windows. So it's a cross-platform IDE. But there are many more IDE that you could use when you work with C programming. The examples I show is basically you built using command line tools. I'm just having my text editor. I run my programs in the terminal. I use make to compile them. I have the GCC compiler, GDB for debugger. And I have some tool called make depend that can use the make file to build up a dependency tree between all the source code files. Well, basically it helps in being efficient and fast and only compiling the files that actually need to be recompiled. And when you have a large system, well, that's actually quite helpful. This is just a view of the code blocks IDE. Looks like any general IDE that you could use. You usually hit FM to compile and build and sort of run it, or you can run it in the debugger. These IDEs, they usually have their own setup of the project's files. So when we create, like here, a new hello world or main, we need to sort of say, is this going to be a GUI application, graphical application? Is going to be console application? What type of application is it? So we need to show that in properly, because the IDE will then set up the different sort of executing environment for that particular project. If we need sort of to find out the manual pages for C, one way to do is to use, like I do then, the terminal. So I'm using the man command. The man command is always available when I'm on a Mac or a Unix station. So in the section 3, we can find the sort of the manual pages for the C language itself. So here I'm doing a man -k. I'm searching for something printf, and I'm getting a match on 3 different man pages. And if I'm opening up one of those, I get the man page for printf. And this is how a man page looks like. So it's describing the functions in it, it's describing what header file is from. I can see what type of arguments I can use when I'm calling the function. And if I continue reading, I will see examples on how to use them. So this is a very good, when you have your system, you might have also included the manual pages. And this is a resource to look for when you're working with C. If you are on, for example, a IDE, then this might most likely be included in the help section and can then also be rather easy to access and search through. So that is a good thing with the IDE. The IDEs might also have, when you sort of hold your mouse over sort of your own source code, and then it can sort of make adaptations to actually review the code to see if you have written the printf in a good manner or not, or give you hints on how you should fulfill a particular function call. So the IDE might help in many of those circumstances, helping in being a productive programmer, basically. Let's look a bit about behind the scenes. And let's introduce ELF. So here I again compiling and linking my program, and it's my directory in this case is then containing makefile, the executable, the object file, and the source code file for C. And if I'm checking those out with the file command, I will see that both the makefile and the C file, that are text files. Then I see this a.out, that is an ELF file. Okay, it was executable and it has some kind of x86 architecture. And same applies for the O file. It's ELF, it's relocatable, it's x86 architecture. And so both these, the object file and the executable, are then sort of ELF files. So if I want to dig a bit deeper down to this, I can see here. So I'm just trying to inspect my own system. So I start with the command uname there. So I'm seeing what type of architecture I'm on. I'm doing file to see what all the details on these two executable object files, or at least a.out is executable, the other is just an object file. So I see that these are ELF files. I'm checking the size of both these, and the size gives me the size of the whole file, and it also gives me the size of different sections in the file. Then I'm doing a hex dump for both a.out and hello world, and I'm seeing that both files start with an .elf. So it's starting with the same signature, and that signature is specific, saying this is an ELF file. So many files have this type of signature, sort of allowing to let the system know what type of files it is. And the last hex dump there, I'm just dumping the a.out file. I'm grepping for the hello string, and I'm finding the hello string there. It's like it's available within the binary. So the string is actually available in the binary. Sounds reasonable. We can also see if we really look at this hello world, and then it comes a dot there, and we see that that dot represents by a 0, 0. So that is the end of the string. It's the \0, the null terminator character for strings. If I further want to dig down, I can look what is ELF file and how does it look like. So here I'm using the readelf command just to check out what is the size, well, details about this particular ELF file. So I'm reviewing its header. And if I further want to study the ELF file, it has some kind of layout. We see the ELF header at the top. Then we have a program header table, and we have a section header table. And these two header tables will point into different sections of the files. So there are many different sections, and we can review a few of them here. Some ELF sections where we have the .text. That's where the code lives. So here is the actual object machine executable code. Then we have a .data where the global tables and variables might be defined. We have a .bss, block starting symbols, and that is for uninitialized arrays and variables. They are to be initialized when we run the program and usually should be filled with zeros. We have an RO data sections where our strings are, and I guess our hello world string would be there. And then we have a few other more type of sections containing different aspects of, well, the executable in this ELF file format. So here I'm further investigating the ELF format. I'm using the object dump command on top there, and I'm extracting the .text section. And here we actually see sort of disassembled code from the machine code, and we can see the assembly code there, what actually happens. And if we really want to dig down and troubleshoot, well, here we can do it to see, well, on some systems we really want to see what type of sort of assembly code is generated. So yeah. Here are two other sections. It's the .data section above there, and then I'm having the RO data sections at the second where, and then again I see the existence of my hello world string, just to get a good grip feeling of how it all looks like. Let's have some notes on the memory layout of a C programming. So when we execute the program a.out, we have a loader. So the system has a loader that loads the executable ELF into memory for execution. And when it does that, it will add a heap and a stack. So those two memory parts. It will positioning and start the program counter, and then the CPU sort of reads the instruction by instruction and executes the sort of code. And if we should sort of try to visualize this, we see here an image that having the ELF file image above. You see the ELF header, and you see some of the sections, and you see the code sections and the data sections. And when we then try to execute the ELF, the loader takes a part of the ELF file, those sections for the code and data, and they put them into an executable in memory. So this is the actual process. And within this process, we're adding a stack and a heap. Here is another image of the memory layout of the process when it's actually running in our system. So at the bottom there, we see the text, that's our code. We see initialized data, we see the uninitialized data, and so those parts come from the those parts come from the binary itself, and then we add a heap and a stack. So heap grows up, stack grows downwards, and this is actually the memory layout. So if we, like we told before, if we should generate a core dump of this process, well then this is the layout that we could actually expect that the core dump file will sort of be structured to. So I think it's quite interesting. And there we go. That should be enough for today. You should now be able to do this on your own. So start somewhere here. I have added a few features to my Hello World program. So I'm having this main program here. I'm now returning an integer, since that is in general what we do. A program like this should return an exit status. It is. So in general, an exit status of 0 is success, and an exit status of 1 is a failure. So, or an exit status of a positive integer is actually a failure. So in this program here, I'm doing exit with exit success, and if I would look in the header file, I will find out that there is a define saying exit success is defined to 0. And there is also exit failed that is defined to 1. I could look that up in the header file. So this is just printf world exit 0 success. And currently I'm not using the argc and argv variable. That is variable. So if I were executing this a.out and I will send some arguments on the command line, these arguments would be sent into my programs, and argc would be the number of arguments, and argv would contain each argument in an array. So then I can create a program that takes arguments or options, and I can sort of execute it accordingly to those. So this is just the way how it should look like if you compile it using make or gcc or your IDE, don't mind, whatever. and execute it. And the last one there is just showing off how you can echo the exit status of the last program executed. So the exit status here is dollar question mark, and this is for a Unix or a Mac that you use this. You use another way if you want to do the exit status if you are on a Windows or Windows terminal. And that should be the end of it all. And thank you for watching. This was in general an introduction to the C programming language. And we also looked a bit behind the scenes on how does the compiled object a.out look like, and how does it work when we actually load it into memory. So I do hope that this is sort of good information now that you are going on towards your journey into the C programming language. So thank you for today, and I will see you soon in another session. Bye bye.